So circular motion, often called centripetal motion. And Jason, as I said already, now that you're putting your phone away, this is where Physics 12 begins. And so here's my first question. Clay already thinks he knows the answer. Is it possible for an object to have a constant speed and yet still be accelerating? Now Clay says, I think the answer is yes, because otherwise why would Mr. Newick be asking me? Which is, again, a valid reason to pick the answer, not a proof, though. Is it possible to be traveling at a constant speed and yet still be accelerating? Yeah. Convince me.
But it's not possible to travel at constant velocity. The speed is not acting from the direction.
So how else can you accelerate? Not just by changing your speed, but also by changing your direction. And in fact, Kohei, now that you've opened that, that's the situation when you're moving in a circle. So if I spin this around, I'm roughly going at a constant speed. It's pretty close. It's taking about the same amount of time to go around in a circle each time. I'm eyeballing it, but I'm pretty close. So let's assume I'm getting it around at exactly a constant speed. It is changing direction. The other reason I know there's an acceleration is because F equals ma. I can feel a force acting on my hand right now. The only way I can have a force, there must be an acceleration. Has to be. So can you be moving at a constant speed? Yes. Can you be moving at a constant velocity? No. And so what we're going to have here for circular motion is a situation where we're going to deal with moving at constant speed in a circle. We're going to call it uniform circular motion. We're not going to accelerate. We're not going to change the speed also while going around in a circle. That gets yucky and you need calculus. All of our circles are going to be nice smooth circles. The velocity is still changing because its direction is changing. And if the velocity is changing, Jason, the object must be accelerating. In fact, this is the most important fact to keep in mind about circular motion. Mitchell, if you're moving in a circle, you must be accelerating. Oh, and since you have mass, there must be a force, because F equals ma. Leads to a question. First of all, we're going to argue that when you're moving in a circle, your velocity is what we call tangent to the radius, perpendicular to the radius. You are moving at a 90-degree angle to the velocity. As I'm spinning this around, okay, let's suppose that I could freeze time. I'm going to spin it faster and faster. If I froze time when the mass was right here and I snipped the string, so it's going like this, which way will this move? See, a lot of people think it's going to go shooting towards Dustin because they've stood on a merry-go-round as a kid, or they've gone around a corner and they think that they're being forced outwards, and you are not. That is not the case, and that's something I'm going to have to lovingly beat out of you. So let's see if we can figure out this direction. To find the direction of the acceleration, we're going to perform a vector subtraction. Huh? Yeah, we know that VF equals VI plus AT. So A equals VF minus VI over T. We've been using that since Physics 11. And since time is a scalar, the direction of the acceleration, Jason, comes from those two vectors subtracted. Technical comment, we're going to show that our acceleration isn't totally constant, and so this relationship is only true for a small time interval. That's okay. We can define the direction then from this, because dividing by delta t isn't going to change your direction. So let's try it. Here's a lovely picture. I have VI, and then like a tenth of a second later, we're right here, and here's VF. I want to subtract these. Well, first of all, how do I subtract vectors? I don't. What do I do instead? So this is really going to be VF plus negative VI. It's going to look like this. VF plus. Now, I think VI is a little, you know what? Let me be clever. If you guys are committed, that's okay. It won't wreck things, but I'm going to put the VF on that side. I'm just visualizing the triangle. It was going to be in the way. No. VI is this way. What would negative VI look like? That way. Yes? That way. Yes? And the resultant is that way. The resultant acceleration is that way, toward the center of the circle. When you're moving around, and this is going to be the single key idea of this whole unit, because when you're moving around in a circle, you're accelerating, but you're accelerating towards the center. This is very tough for non-physics people especially to wrap their brain around, because they want to say, no, I'm accelerating outwards because I'm being pushed outwards. No, what you're feeling, so ever been on a merry-go-round as a kid? Okay. Ever stood on the very edge and held on to it and had your friend spin it fast? Okay. Your body has mass. It wants to keep going in a straight line on a steady speed. That's Newton's first law. But to go in a circle, you have to accelerate in which direction? Towards the... Now, the reason you felt like you were being pushed out was actually your arms were having to pull in. They were exerting the force accelerating you towards the center. Your arms were actually pulling in towards the center. It's just because your bodies are backwards accelerometers, you feel like you're getting pushed out. If you're moving in a circle, I'm telling you, Spencer, you're accelerating towards the center. You're accelerating towards the center. So, we see that an object moving in a circle is accelerating towards the center of the circle or accelerating inwards. In fact, we have a fancy phrase for it. We call this centripetal. Now, you may hear some people talk about centrifugal force with an F. No such thing. That's the feeling that people get when they're getting pushed outwards, and they think that that's because they're getting pushed outwards. No, it's because they're having to exert a force inwards to accelerate themselves inwards, and they're not used to doing that, so they think the reason they're having to exert that force is, I must be getting pushed out. In fact, centripetal literally means center-seeking. Centripetal force is a center-seeking force. It points towards the middle. So you're going to hear me talk about centripetal acceleration, circular acceleration. We're going to, Kiowa, be able to use a lot of our Physics 11 stuff, but we're going to have to modify our acceleration equations. Suppose a ball was on a frictionless tabletop and it was rolled along a circular track as shown as seen below in the top view. So the ball is rolling like this. The track is not a complete circle, and the ball leaves the track right there. What path does the ball follow after it leaves the track, A, B, or C? Hey, this is a chance for us to vote. Once again, how high you hold your hand up is how sure you are of the answer. Okay, so we're looking down. This is the top view. We're making the ball, for you guys, move around the track, and then it hits the gap. Who says A? 1, 2, 3, 4. Who says B? Who says C? Was that a hand up, Kiowa, or that was just like, okay? C is the one a lot of people will think because they've been on merry-go-rounds as children, okay? And they have felt that force pushing them out. Sorry, let me be careful. They have felt their inertia, because it's not a force, their own inertia wanting to keep going in a straight line at a steady speed, but because the merry-go-round starts to move away from them around the corner, they've had to exert a force, and they think, oh, I must be getting pushed out. Convince me. Yeah. So, what's your point? So, what's that mean? I'm looking for a key word. Why can't A be right? What? What? Clay. There would have to be an outside force, because is it changing direction? We said you can accelerate by changing direction. There would have to be a force acting on A. If it's left the wall, if it's left the track, there is no longer a force. Now it'll keep going in a straight line with steady speed. Path B. Path B. Next page. So, why is the acceleration inwards when the push that we experience in a car seems to be outwards? You've done a left-hand turn in a car and you feel like you're being pushed to the right. Why is that? Well, you're not. What's really happening is inertia. Newton's first law says your body wants to keep going in a straight line at a steady speed. But if the car is going to follow this path, it has to apply a force on you in order to make you change your direction, accelerate, and follow that same path. You're not used to a car applying a force on you, so you think, oh, I must be getting pushed out. It's not what's happening. It's the car applying a force on you. Is that okay? Did I tell you the grandfather story? I might have done this when we looked at forces or in Physics 11. Talk to your grandfather, especially if your grandfather used to slick his hair back in the day and went on lots of dates. Back in the 1950s and the 1960s, when cars had bench seats, not bucket seats, and when seatbelts weren't worn. If you were a high school kid and you were going out on a date, ask your grandfather. He may fess up or he may know of somebody who did this. You would put surfer's wax on the passenger seat. And then what you would do is you would drive with your left hand on the wheel and your right hand you would have up on the bench seat, and you would make a quick right turn. And the girl would come sliding across and, oh, excellent. And then you went, well, thank you, honey. And then you would keep going in a straight. Was the girl really sliding across? No. The girl was going in a straight line at a steady speed, Newton's first law. The car was moving underneath her and having her intersect the male driver. Okay? Ask your grandfather, he may fess up. So, from the point of view of the driver inside the car, this straight line motion seems to be outwards. But you actually want it. So in other words, if you let go of the merry-go-round, you would fly this way, not that way. Put your pencils down. Well, Clay, this discussion is really important because many years of experience in a car or as a child on a merry-go-round leads non-physics people to believe that there is an outwards pushing force. There is not. All that is your own inertia, or the object's inertia, the object's mass, wanting to keep going in a straight line at a steady speed. But then you, if you're the person, have to apply a force in, or the car door, something has to apply a force on the mass inwards to keep it moving in a circle. In fact, there's even a term called centrifugal force with an F, which refers to this apparent outside push. Garbage. It's not a force. It's merely inertia. And it's not outwards. It's actually in a straight line tangent to the radius, as you saw with the videos that I showed you. They did not fly straight out. Have I got you? So if fighter pilots move too fast in a loop, they can become unconscious due to a lack of blood flow to the brain. And some people say, oh, it's because the blood got forced to their feet. You're not on your phone or anything foolish, are you, back there in the corner? No. Put the phone away. This is sometimes attributed to centrifugal force. What's really happening here? This is a job for a picture. Here's Mr. Duick's plane picture. Okay? What I really want you to notice is, here's the fighter pilot. And all I care about right now is his torso, because that's where the blood is. Okay? Now, he does also have feet. He also has a head. So let's add a brain, because we need blood in the brain to stay conscious. Here's the blood. The plane is traveling in this direction, and then it starts to pull up. What direction does the blood want to keep going? Straight line, steady speed. Because it's liquid, it can. So when the fighter pilot gets to right here, all of the blood has gathered in his feet. Now, we say that the blood got forced down from his feet. No, his head got pushed away from the blood, which kept going in a straight line at a steady speed. That's the danger. So in World War II, during the Battle of Britain, there was a British pilot. I mean, Britain needed every single pilot. And there was a British pilot that was shot down, and he survived the crash, but as a result of the crash, they had to amputate his legs above the knee. But he was otherwise healthy, and they were desperate for pilots. And so what they did is they retrofitted a plane. They lengthened the pedals, and he could use the pedals with his thighs, and he went up and he flew again. And he realized that he could dive faster and pull up sharper than anyone else. And so what he would do is he would let the German pilot get right behind him, and of course pilots are fairly macho, and if you can do it, I can do it, and he would dive down to the ground, and the German pilot would fall. And then he would pull up really fast, and the German pilot, well, if you can do it, I can do it as well, would pull up and would black out and hit the ground. And the story goes that the German pilots actually memorized this pilot's serial number on the plane, and they would radio each other, hey, don't follow him, he can do something, we don't know what's going on, but he can do something we can't. Okay. True story. Or if you want a more modern twist, put your pencils down. We'll finish with this. So how do we calculate circular acceleration? Here's your equation that you'll be flogging to death during this unit. The proof is a bit long, so I'm just going to give you the equation. My A for acceleration, and then I put a little C for centripetal or circular acceleration. Technically centripetal, but you can remember C for circle is a dumb way to remember. It helps. I'm leaving the vector off. There is a direction, but I'll tell you what the direction is. Always towards the, but it depends where you are in the circle. That's a different direction, because if you're on that side of the circle or on that side of the circle. So I'll leave the vector sign off. If I ever ask you for a direction, you'll just say towards the. Okay? It's equal to v squared over r. The speed of the object squared divided by the radius of the circle. This is also why you saw the tourist blacking out. Again, we have this squared thing. Twice as fast means 4 times the acceleration, 4 times the force is going to be required to move you in a circle. So those fighter pilots are pulling an awful lot of G's. Okay?